Good morning, everyone. Now we are going to see the next part of Miller indices. Now let's see example of how to draw a plane from Miller indices. As we had already seen in the last lecture, example like 100, if this is my unit cell, this 100 indicates that the intercept is 1 along x-axis, 0 along y-axis, and 0 along the z-axis. So first we have to take the reciprocal of all these numbers. So if I take the reciprocal, this would become 1, infinite, and infinite. That means intercept is 1 along x-axis and y and z-axis intercept is at infinity. So the plane which I am going to draw, that has to be parallel to that particular coordinate axis. Let us mark the origin as well as x, y and z. This x, y, z are arbitrary. You can change the positions of x, y, z also. Okay. Now x is cutting at one point. So this is the point where if this is the origin, x is 1 here. Y is also infinity, z is also infinity. So I need to draw a plane or find a plane such a way that it is parallel to both my y-axis as well as to my z-axis. Right. So these are the lines which are parallel to my y-axis and these are the line which are parallel to my z-axis. So this is what is my 100 plane. Clear? Now we'll see another one example. Let us draw for 1, 1, 0. So for 1, 1, 0, x-axis also it is cutting at one point, y-axis also it is cutting at one point, and z-axis it is at infinite. Right? So now let us suppose that this is my origin, this is my x, this is my y, and this is my z-axis. Of course, I take the reciprocal, so this would become 1, 1 and infinity. So x it is cutting at one point, y also it is cutting at one point. So I have a line along the back face. Just now I need to draw a line opposite to this line in the front face. So this is what is my 110. Okay. Now let's have another one example with the bar 100. So here x-axis it is at negative axis representation, right? Bar is indicating that x it is actually cutting at minus 1 point here. Okay, so let's do a very small change here. If I take this as my origin, this point will become 1. Now I want minus 1. So what I do is just let me change the position of my origin alone. Instead of taking origin here, I take my origin here. So this point now would become minus 1. So this is now my minus 1. And the plane which I has to draw now, that has to be parallel to both my y as well as z. So these are the lines which are actually parallel to my y-axis and these are the lines which are parallel to my z-axis. So this is what is my bar 100. Okay. And one more last one. Suppose if anything other than 1 come. Suppose if it is 1, 2 and 1. Now how to draw this? Of course, the first thing, don't forget to take the reciprocal of those numbers first. Okay. So if I take the reciprocal 1 to 1, it would become 1 half and a 1. Right. So x-axis it is cutting at 1 point. Y-axis it is cutting at half a point and z-axis it is again cutting at 1 point. So x it is at 1, y it is at half, so the entire length is 1, so y half will come somewhere here and z is also 1, so z will 1 will come here. So now draw a plane connecting all these 3 points. This is what is my 1 to 1 now. Okay, I hope how to draw a plane is clear now. Now let's see what are all the important features of Miller indices. Okay. So the first point which is already known to you, if a plane is parallel to any one of the coordinate axes, the intercept is set at infinity. Hence the Miller index for that particular axis is 0. For example, we had seen cases like this where When any one of the Miller indices value it is 0, that means that the intercept is at infinity. So the plane which I am going to draw, that has to be parallel to that particular coordinate axis. This is what does this mean. Okay. And the plane passing through the origin have non-zero intercept. If you would have remembered, I had already told you that 100 is a plane which is any one of the face of the cube. 110 is something that is passing through the face diagonal, and 111 is something that is passing through the body diagonal. So a plane which is passing through the origin definitely would be having non-zero intercept. And all equally spaced parallel planes have the same Miller indices only. As it is already told to you, Miller indices do not define a particular plane but a set of parallel planes only. So all equally spaced parallel planes, they have the same Miller indices. Also, the ratios like 844, 422, 211, which are all the same, they do represent the same planes only. Okay. And if a plane is cutting the negative side of the origin, of course the corresponding Miller indices will be negative. These points we had already discussed while we draw the Miller indices planes representation. Now we come to the next important part of Miller indices, which is interplanar spacing. The word itself clearly tells you that interplanar distance means it is the distance between two planes. Okay. So we focus mainly on parallel crystal planes here, and we know that they have the same Miller indices also. So the spacing between these parallel planes is called as interplanar spacing, and we denote it by the letter D, and HKL or the Miller indices value. So our aim is now to find an expression for interplanar spacing. That is, we need to find a mathematical expression for D. For that, let us consider a unit cell, and let us consider a plane ABC which cuts x-axis at A point, y-axis at B point, and z-axis at C point. Now, let us imagine that there is another one plane which is passing through the origin. And our aim is actually to find the distance between the two planes. Let us drop a normal here in such a way that this ON represent D, which is nothing but the interplanar distance. I repeat, our aim is actually to find interplanar distance, that is the distance between two planes. For that, let us consider a plane ABC, and let us imagine that there is another one plane which is passing through the origin, and our aim is actually to find the distance between the two planes. We are dropping a normal here in such a way that it makes an angle alpha with respect to x-axis, beta with respect to y-axis, and gamma with respect to z-axis. And so ON represent the distance between the two planes. Okay, this is very clear in this diagram. This is what is our unit cell. ABC be the plane here, and ON be the normal we had dropped, and alpha, beta, gamma are the angles in which the normal makes with respect to x, y, and z. So from the figure, it is very clear that cos alpha. How will you take cos alpha? Cos alpha is from the triangle ONA. So if I consider triangle ONA, my cos alpha, it is nothing but ON by OA. Right? This ON by OA is nothing but a cos alpha. Similarly, I can write what are the values of cos beta and cos gamma also. Of course, cos beta, I have to take triangle OBN. It is very clear. So cos beta, it is nothing but ON by OB, where OB is the hypotenuse here. Okay. Of course, cos gamma, I need to consider triangle this OAC here. And now that is nothing but ON by OC. That we can write it as D by OC here. Okay. So we found what the values of cos alpha, cos beta, and cos gamma. They are nothing but D by OA, D by OB, and D by OC. Simple trigonometry relation, we know that cos square alpha plus cos square beta plus cos square gamma is equal to 1. So we are correlating, we are going to correlate that. So for that, first we need to find the values of OA, OB, and OC. So we know by definition itself, Miller indices, OA is to OB is to OC, it is nothing but A by H is to A by K is to A by L, where A, B, C which are the lattice parameters for a cubic unit cell. They are the same, so I had represented only it by A, and HKL are nothing but your Miller indices value, right? So these are nothing but your OA, OB, OC. Now I substitute the value of OA as A by H here. So cos alpha would become DH by A. Similarly, cos beta would become dk by A, and cos gamma would become dl by A. As I mentioned, we use the trigonometry relation. This is equal to 1. So cos square alpha is dh by A the whole square, cos square beta is dka by whole square, and cos square gamma it is dl by A the whole square, which is equal to 1. So d, it is nothing but A by square root of h square plus k square plus l square. This is a very simple relationship connecting interplanar spacing and lattice constant. Now, we know that 100, 110 and 111 are the plane which are very, very important because this gives information about the length and this gives information about phase diagonal, and 111 of course will give information about your body diagonal, right? So we can actually find the ratio connecting these three numbers. So D110, it is nothing but A by square root of h square plus k square plus l square. So here h is 1, k and l are 0. That means this is nothing but A by square root of 1 square, which is nothing but A. Now for D110, H and K are 1 and 1, right? So if I put H and K as 1, 1, this would become A by 1 square plus 1 square, that is nothing but A by root 2. Now, if I write for D111, HKL values are 1, 1 and 1 again. So 1 square plus 1 square plus 1 square, it is nothing but A by root 3. So if I find the ratio between D100, D110 is to D111, it is A is to A by root 2 is to A by root 3, or I can write this as 1 is to 1 by root 2 is to 1 by root 3. Okay, this is what is a ratio among the interplanar distance for actually a simple cubic crystal structure. I hope you understood. We found the mathematical expression of D to be A by square root of h square plus k square plus l square. Now we are going to consider these three planes 100, 110 and 111. I substitute the value of HKL as 1, 11 and 111 in the 3, and I found the ratio of this to be 1 is to 1 by root 2 is to 1 by root 3. So if the ratio comes to 1 is to 1 by root 2 is to 1 by root 3, this means the crystal we are dealing with a simple cubic crystal structure. I hope this is clear. Thank you everyone.